So here we are. We have this algorithm that finds the largest element in an array, right? Returns the value of the largest value in an array. How do we analyze this? Right? How do we use the tools we've learned so far to come up with a complexity class for this? Well, we've done this once already in the last set of lectures. We've done, or I guess we've done this twice actually. We did this for the Tower of Hanoi also. But what we do is we say, hey, look, we need to write a recurrence relation for this recursive algorithm that expresses the number of basic operations that get performed. Okay, and so here, what's our basic operation? Well, let's call the max check our basic operation, right? So what it's doing is it's checking to see, it's comparing two values and returning the one that is larger, and that's a non-trivial operation. So that'll be our basic operation. So this line here essentially captures the number of basic operations that have to be performed on an array of size n. And then this line here says, hey, look, when we get to this return statement and we make a recursive call, we're performing a basic operation. In addition to the basic operation of maximum, we're also performing a recursive call. So we're making a recursive call on the left half of the array, and we're making a recursive call on the right half of the array. T of n over 2 again. Okay, so this one corresponds to the left half, and this one corresponds to the right half. And this is our recurrence relation, right? So we have an overall recurrence relation that looks like the following, and I'm going to scroll down to here to discuss it. So our overall recurrence is this. T of n equals 2 t of n over 2 plus 1. And this is a kind of a format that you'll become very familiar with as we think more about divide and conquer algorithms. So the format says this. I am making two recursive calls. Right? And so this corresponds to the number of chunks or of subproblems I have to solve. So the number of chunks in my divide and conquer algorithm. This one corresponds to the size of each chunk. Okay, so this is the size of each chunk. Okay, so each chunk is half the size of the original array. And then the plus 1 here corresponds to all the overhead, right? All the extra stuff we have to do to be able to make this computation. So this is our recursion overhead. All right. So here's our recurrence relation. I believe we've done something like this in lecture. If we haven't, or if you don't see it immediately, what the complexity class of this is, pause the video, work it out, make sure that you know what this is. Make sure that you know what this is doing. So the complexity of this particular recurrence is linear, and we can actually reason why this must be the case. Okay, so let's think about how many items get compared when we do this algorithm. Okay, so I'm gonna do a very informal explanation of why we have a linear time complexity here. So suppose I have an array with 8 things in it. So 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 elements in the array. What is this algorithm going to do? Well, it's going to make a comparison. This is logically speaking, this isn't between values. It's going to make a comparison here. In fact, I'm going to do this in a different color. So it's going to make a comparison here. And then what's next? Well, it'll make some comparisons here. We think about splitting those up. And then what will it compare? Well, it'll compare here, 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 and here. Right? So in between each pair of elements, you can imagine, logically speaking, you can imagine a comparison. So it isn't actually comparing every single pair of elements, But if I were to write it out like this and think about what's actually happening as the recursion goes, this is what it would look like. I would get one comparison that shows up in between each pair of elements. Right? It's not literally comparing those two elements. Like it may not, this comparison might not actually compare this with this. Right? This center comparison here is comparing the largest thing on the right with the largest thing on the left. And I don't know a priori which one of those things there's going to be. But I do know that in terms of, in between those two array indices, I can think of that as being a single comparison that happens. Right? So this algorithm will always perform exactly n-1 comparisons. Right? There's one in between each of the array elements. And therefore it is a linear time algorithm. All right, what about more complicated recurrence relations? What about more interesting, kind of more complicated divide and conquer algorithms? What might we see? Well, in the next video, we'll start to think about what else there could be that might satisfy this divide and conquer kind of philosophy.